Turbocharging GPU inference at Logically AI. Maria, this blog explores how we can achieve better model inference performance for big GPU based models on Databricks. So let's start with the problem statement. What are we trying to solve here?
Yeah, so this blog is a blog we co-authored with Logically AI, as you said. And what was the challenge we had is given a GPU model, that in this experiment, actually, we had no clue what this model was doing behind the scenes. We don't care about that. Given any GPU model, what are the tricks and what are the things you can adjust on Databricks to make this batch inference job run as fast as possible? So that was the challenge.
Awesome. And so what did you try here? Because I can see fractional GPU allocation. Can you explain a bit more what it is?
Yeah, so if you take anything out of this video and of this blog is to understand this fractional GPU allocation. So what happens is that if you would think that this is our cluster and a cluster on Databricks is a Spark cluster, so it has the driver, and in this case, let's say it has two workers, and in each worker we have two CPUs and one GPU. So as a total in the cluster, we have two GPUs and then four CPUs to utilize in terms of compute. When we run a Spark job on a GPU cluster like this one, what happens is that by default, Spark creates and allocates one task in each GPU. So each GPU of this multi-node cluster will run one only task. Now, why is this a challenge? Is because if these tasks are small, then GPU is not utilized enough. It could run multiple more tasks in parallel, but because of this default configuration of Spark, we cannot do that. So what we're trying to do here is fraction this GPU, as we say, and instead of just pushing one task per GPU, allow the GPU to run multiple tasks. And in order to do that, you have to play with this task.resource.gpu. And instead, by default, it's equal to 1, which forces one task to be run in its GPU. But then you can start experimenting with different percentages, saying that allocate 25% only of this GPU to a task. In this case, it could run multiple tasks in parallel. Of course, this is something that you have to configure and see how your workload works, given the GPU number and the GPU sizes you have. But this gave the best results, as in the best uplift in terms of reducing the latency just by switching and manipulating this configuration. So allowing more tasks to run in parallel in each GPU.
Interesting. So basically, you're just trying to make the most out of your GPU, which are expensive, yes, right? And so what you did here as a first experiment is allow more tasks to run in parallel on each GPU. What else did you try to optimize, to optimize even more, like the GPU utilization?
Yes, excellent. So the first thing, as we said, is how we can run multiple tasks in the GPU. So how we can increase the parallelization of the GPU. The other thing you can do is on the task size. So how can we push more data into this task and make it a bigger job? So as well as running in parallel things, running bigger chunks of data in each task. So there are multiple things to try here. In our case, we tried Coalesce because we had already the data in memory and we just wanted to merge partitions. But basically what Coalesce does is, given some partitions of data that you have, and each partition is associated or run in its task, we kind of merge these partitions and create bigger partitions. So what this does is, if you see here the graph, is we kind of create bigger partitions of data, so bigger chunks of data. But one thing to consider here is that we cannot just keep merging partitions, because at some point, like, the GPU will be out of memory. So while you manipulate these, you have to be aware of out-of-memory errors on the GPU. And there are different ways to manipulate that, as we'll see later on how we dealt with these from the read side of the data. So in this case, what we did is that coalescing and bringing together, the partitions, creating bigger partitions at this case by reducing the number of default partitions of Spark. So we did that with Coalesce in this case, but you can also do something similar with Repartition as well.
Got it. So just in a nutshell, to fully utilize the GPU, you wanted to create bigger partitions so that you can allow each task to manipulate more data. In order to do that, you leverage Coalesce, as you explained here. There are also other strategies. Amazing. And if we want to put a system like that in production, Coalesce may create some issues in terms of partition size and if it fits in memory, etc. So is there any way to control it?
Yeah, excellent question, Lara. So as we said, Coalesce, what it does is as the data are kind of read into and split into partitions, we kind of merge them, which this means that some of the partitions may be bigger than others, some skewed data, etc. So which means when you merge them, you may create really unbalanced partitions. And this is something that Repartition solves for us if you go through the blog. But the other thing you can do is start manipulating the partition size from the beginning, from the read operation of Spark. And we did that in this case with Mar partition by. So we're saying that by default, it's 128 megabytes by default Spark configuration. What we said now is let's bring from source bigger partitions. So instead of us then having to merge and manipulate partitions later on. So just let's read from start bigger partitions into our process and then start using the GPU fraction instead of having to deal with Coalesce or Repartition later on. That allows you to have like an upper limit of the partition so that you make sure your production job is never overloaded with data and breaks because of GPU out of memory errors, for example.
Awesome. And final question from me. What is the difference between this and using Ray on Databricks?
Very interesting question. So if you see here, the next steps that you can try is actually started incorporating Ray into this process. This process, mainly Ray comes into the GPU fraction that we said before and how you can have a better control and understand the resource of your cluster. So you could have implemented the GPU fraction, for example, here with Ray. Ray allows you to do that. It's an extra layer that you have to maintain. And in this case, we didn't want to have Ray as in the first iteration of this experiment. So we wanted to understand our compute, our resources, and just work on Spark at this point. But given this Spark cluster, you could create on top a Ray cluster and start manipulating the resources through Ray now inputs.
Amazing. Thanks, Maria.
Thank you, Lara.